The universe is not a random scatter of galaxies drifting through emptiness. It is a vast, interconnected structure, an immense, mathematically ordered network stretching across billions of light years. Astronomers call it the cosmic web, colossal filaments of matter threading through space, enclosing immense voids and converging at dense nodes where gravity warps space-time itself. For decades, this architecture existed only as a hypothesis, hinted at by partial observations and theoretical models. But recent advances have changed that. Large-scale surveys and powerful telescopes have begun to map the web in unprecedented detail, tracing millions of galaxies and peering deep into cosmic history. What emerges is both precise and unsettling. The web appears larger, earlier, and more coherent than current models predict. Some structures span distances that challenge accepted timelines. Others display patterns, alignments, and symmetries that remain unexplained. We set out to map the universe. What we found instead is a structure that may be far more ordered and far less understood than we expected. The universe was not supposed to look like this. Before the first large-scale galaxy surveys, the universe was expected to be, at the largest scales, essentially uniform. The cosmic microwave background, the oldest light in the universe, is uniform in temperature to within 1 part in 100,000 across the entire sky. This extraordinary smoothness indicated that the early universe was smooth. The density variations that seeded all subsequent structure were present, but tiny. Fluctuations of 1 part in 100,000 in the density of the primordial plasma. From such tiny seeds, gravity was supposed to grow structure slowly and progressively over billions of years, building small clumps first, then merging them into larger ones in the hierarchical assembly process called bottom-up structure formation. The expectation, reasonable and well-motivated theoretically, was that at the largest scales, the universe would look homogeneous and isotropic. Small fluctuations from place to place, reflecting the random distribution of galaxy clusters, but no organized large-scale structure of the kind that would require specific physical explanation. The universe was supposed to be, above a certain scale, a statistically uniform sea of matter with no preferred directions, no large voids, no enormous connecting filaments. The cosmological principle, which undergirds the entire mathematical framework of modern cosmology, states that the universe is the same everywhere and in every direction at sufficiently large scales. The universe was supposed to be boring at the top. The first hints that this expectation was wrong came from galaxy redshift surveys in the 1970s and 1980s. When astronomers began measuring the distances to thousands of galaxies and plotting their positions in 3 dimensions, they found that galaxies were not distributed randomly. They clustered into groups and clusters, yes, as expected. But they also appeared to lie on sheet-like structures and in chains, with large regions between them that appeared to be almost completely empty. The most dramatic early confirmation came from the CFA redshift survey in the 1980s, particularly from a slice of the universe that showed galaxies concentrated in a thin, curved structure surrounding a nearly empty void, a pattern that became known as the CFA Great Wall. When Margaret Geller and John Huckray published the CFA survey results in 1989, showing the large-scale distribution of thousands of galaxies as a slice through 3-dimensional space, the scientific community was looking at the first clear image of what would come to be called the cosmic web. The galaxies were not distributed uniformly. They were connected in filaments. They clustered at intersections of those filaments. And between the filaments were voids of striking emptiness, regions tens of millions of light years across, containing almost no galaxies at all. The universe had large-scale structure of a kind, and on a scale that the theoretical community had not anticipated. The subsequent 2 decades saw the rapid development of survey technology and theoretical framework in parallel. Cosmological simulations, running on increasingly powerful computers, began to produce synthetic universes from initial conditions, consistent with the cosmic microwave background, and let them evolve forward in time under gravity and dark energy. The simulations produced cosmic webs. The filamentary structure emerged naturally from the mathematics of gravitational collapse operating on small initial perturbations. The agreement between simulations and observations, at least in broad outline, was one of the great successes of computational cosmology. The cosmic web was not an unexplained anomaly. It was a predicted consequence of the physics of structure formation, and when the simulations were calibrated against observations, the agreement was striking. But the agreement was not perfect. It was never perfect. And as the surveys grew larger and more detailed, the specific ways in which observations deviated from simulations became increasingly clear and increasingly difficult to dismiss. The structures being found were consistently larger than the simulations predicted at equivalent epochs. The voids were consistently deeper and more precisely shaped than the simulations produced. The alignments between galaxies, between galaxy spins, and the filaments they inhabit were stronger and more coherent than any simulation naturally generated. The universe, it turned out, had organized itself more thoroughly than the physics was supposed to allow. What the cosmic web actually is. The cosmic web is the largest known structure in the universe. It is not a single object. It is a pattern, a network of matter distributed across the observable universe in a specific three-dimensional arrangement that has been compared, since its discovery, to a spider's web, to the structure of neurons in a brain, to the foam of soap bubbles, and to the distribution of filaments in a fungal mycelium. All of these analogies capture something real about the structure's character. None of them captures its full extent or its underlying physical nature. At the most fundamental level, the cosmic web is the result of gravitational instability operating on the small density fluctuations that were present in the universe shortly after the Big Bang. Regions of the early universe that were slightly denser than average gravitationally attracted matter from their surroundings, growing denser over time. Regions that were slightly less dense than average lost matter to their denser neighbours, growing emptier. This process, driven purely by gravity acting on quantum fluctuations amplified by inflation, continued for billions of years, eventually producing the structure we observe today. The mathematics of gravitational collapse in an expanding universe predicts a specific sequence of structure formation. The first structures to collapse are the smallest, because small-scale density fluctuations have shorter gravitational timescales. Over time, small structures merge into larger ones in a hierarchical process. Sheets and filaments form as matter collapses preferentially along the axis of greatest compression first. The intersections of filaments become the most strongly concentrated regions, the nodes where galaxy clusters form. The interiors of large underdense regions expand as matter flows out toward the surrounding structure, growing into the voids that separate the web's filaments. The specific three-dimensional structure that results has 4 distinct components, each with its own physical character and scientific significance. The nodes are the densest points, where filaments intersect and matter has concentrated maximally. These are the sites of the largest galaxy clusters and superclusters, objects containing thousands of galaxies, millions of billions of solar masses of matter, and enormous reservoirs of hot gas at temperatures of tens of millions of Kelvin that glow in X-ray light. The Coma cluster, the Virgo cluster, the Perseus cluster, the El Gordo cluster are all node structures in the cosmic web, some of them extending over tens of millions of light years and containing more mass than any other structures in their vicinity. The filaments are the connecting threads of the web. long strands of matter linking nodes across distances of hundreds of millions of light years. The galaxies in filaments are not randomly distributed along them, but show preferred orientations, with their major axes tending to align parallel to the filament and their angular momentum axes perpendicular to it. The filaments also contain warm gas at temperatures of hundreds of thousands of Kelvin, far too diffuse and too cool to emit significantly in X-rays, but detectable through the Sunyaev-Zeldovich effect, the distortion of cosmic microwave background photons by scattering off the hot electrons in the warm gas. This warm-hot intergalactic medium contains a significant fraction of all the baryonic matter in the universe, a reservoir of gas that connects the network and feeds the galaxy clusters at its nodes. The sheets are the two-dimensional structures that bound the faces of the voids, less concentrated than filaments, but more concentrated than voids. Galaxies in sheets tend to be distributed more uniformly than in filaments and show different morphological properties, with a higher fraction of disk galaxies and a lower fraction of the elliptical galaxies that dominate the nodes. The voids are perhaps the most scientifically fascinating component of the web, precisely because they are almost empty. The largest voids are roughly spherical regions, hundreds of millions of light years across, that contain extremely few galaxies. The Bootes void, discovered in 1981, is approximately 330 million light years in diameter and contains only about 60 known galaxies, where the average density of the universe would predict thousands. The voids are not random. They appear to be organized in a pattern, abutting each other and surrounded by the sheets and filaments of the web, creating a foam-like topology in which the empty spaces are as structured and regular as the filled ones. The physical conditions inside voids are unique in the universe. The density of matter is far below the cosmic average. The dark energy density correspondingly dominates, and the expansion rate inside a void is higher than the cosmic average. Voids are expanding faster than the universe as a whole because there is less gravitational deceleration from matter in their interiors. They are also shielded from the reionizing ultraviolet radiation that pervades the intergalactic medium of denser regions, meaning that the gas inside voids retains a chemical state and temperature closer to the primordial conditions of the early universe than gas anywhere else in the present cosmos. The surveys that changed everything. The transition from a rough awareness of the cosmic web's existence to actual detailed maps of it was driven by a series of large galaxy redshift surveys conducted over the past 3 decades. Each survey improved on its predecessors in volume, density and precision, and each one revealed structure on scales that the previous survey had not accessed. Together, they produced what is now the largest empirical data set in the history of astronomy, a 3-dimensional map of the distribution of matter in the observable universe across hundreds of millions of light years in multiple directions. The Sloan Digital Sky Survey, begun in 2000 and still ongoing in successive phases, was the watershed moment in cosmic web mapping. Using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, with a wide-field camera and multi-fiber spectrograph capable of measuring the spectra of hundreds of galaxies simultaneously, SDSS systematically mapped a large fraction of the sky accessible from its location. The survey's strength was its sheer scale. By its 7th data release in 2009, it had obtained spectroscopic redshifts for nearly 1 million galaxies, producing a 3-dimensional map of unprecedented coverage and depth. The map extended to a redshift of approximately 0.5 comma, corresponding to a look-back time of approximately 5 billion years, over a substantial fraction of the sky. The SDSS maps confirmed the existence of structures that had been glimpsed in earlier, smaller surveys and revealed new ones at scales not previously accessible. The Sloan Great Wall, identified in the SDSS data in 2003 by Gott and colleagues, was at the time of its discovery the the largest known structure in the observable universe. A sheet of galaxies approximately 1.37 billion light-years long, 80 million light-years wide, and 15 million light-years thick. Its very existence strained the predictions of the standard lambda CDM cosmological model, which predicted that structures of this length should be extremely rare in a universe of the observed age. Subsequent analysis of large numbers of simulations confirmed that a structure as coherent and as large as the Sloan Great Wall was found in only a tiny fraction of simulated universes with the same cosmological parameters as ours. The Dark Energy Survey, which began observations in 2013 using the 4-meter Blanco telescope at the Cerro Tololo Inter-American Observatory in Chile, pushed the frontier of sky coverage and photometric depth. DES used a 570 megapixel camera, the Dark Energy Camera, to image 5,000 square degrees of the southern sky in 5 optical filters. Its primary scientific goal was the characterization of dark energy through multiple probes including galaxy clustering, gravitational lensing, and galaxy cluster counts. In accomplishing this goal, it catalogued approximately 300 million galaxies and produced the most detailed wide-field photometric map of the southern sky ever made, revealing the projected distribution of matter across vast areas of the universe at depths reaching billions of light-years. The Dark Energy Spectroscopic Instrument, DESI, represented the next leap. Installed on the 4-meter Mayol telescope at Kitt Peak National Observatory in Arizona and beginning survey operations in 2021, DESI uses an array of 5,000 robotic fiber positioners to simultaneously measure the spectra of 5,000 galaxies in a single exposure. The result is a spectroscopic survey machine of unprecedented throughput, capable of measuring precise spectroscopic redshifts and therefore precise three-dimensional positions for tens of millions of galaxies. The first year of DESI data, released in 2024, included spectroscopic redshifts for approximately 6.5 million galaxies and quasars, instantly becoming the largest three-dimensional spectroscopic galaxy catalogue ever produced. The DISI 5-year survey, currently underway, is expected to measure approximately 40 million galaxy redshifts and produce a three-dimensional map of the universe's large-scale structure of a quality and depth previously unimaginable. The Euclid Space mission, launched by the European Space Agency in 2023, has added a space-based dimension to the cosmic web mapping effort. Observing from the second Lagrange point, Euclid images the sky with a wide-field near-infrared camera and a visible light photometer, measuring the shapes of more than 1 billion galaxies for weak gravitational lensing analysis and photometric redshifts for hundreds of millions. The combination of lensing maps and galaxy position maps provides simultaneous constraints on the distribution of dark matter, which neither emits nor absorbs light, and can only be traced through its gravitational effects, and the distribution of visible matter in the form of galaxies. Euclid's survey of 15,000 square degrees of sky to high photometric precision is producing the most comprehensive weak lensing map of the cosmic web ever assembled, tracing the full matter distribution, including its dark component, rather than just the luminous traces. The Great Attractor and the flows that defied explanation. Before the maps confirmed it in detail, the cosmic web announced its presence through a phenomenon that took decades to explain: the anomalous bulk flow of galaxies in our local universe toward a specific region of space far beyond our galaxy. A gravitational attractor of such enormous scale that its existence implied large-scale structure on a scale that the theoretical community had initially resisted acknowledging. In the 1970s and 1980s, observations of the peculiar velocities of galaxies, the components of their velocities that are not due to the expansion of the universe, but rather to the gravitational pull of nearby mass concentrations, revealed a systematic pattern in the local universe. Galaxies over a wide region of sky, including the Milky Way itself, appeared to be moving toward a particular direction in space at velocities of several hundred kilometers per second above and beyond the Hubble flow. The magnitude of the bulk motion required an enormous mass concentration pulling on the local universe, a concentration far larger than any known galaxy cluster. The region toward which this motion was directed lies in the direction of the constellation Centaurus, at a distance of approximately 250 million light-years. It was named the Great Attractor. Its existence was controversial initially because much of the region is obscured by the dust and gas of the Milky Way's disk, making optical observations impossible and forcing astronomers to work with radio, infrared, and X-ray data. But as observational coverage improved, the Great Attractor was identified as the core of the Laniakea supercluster, a massive overdensity of galaxies and galaxy clusters spanning approximately 520 million light-years and containing the equivalent mass of approximately 100 quadrillion suns. The Laniakea supercluster itself is one of the largest known structures in the universe, defined in a landmark 2014 paper by Brent Tully and colleagues using peculiar velocity data from the Cosmic Flows surveys. The paper defined the supercluster not by galaxy positions, but by the boundaries of the gravitational watershed, the region within which all matter is flowing toward the same gravitational attractor. This approach, analogous to defining a river's drainage basin by tracing which direction water flows on every slope, identified Laniakea as a coherent dynamical structure whose interior matter is falling toward the Great Attractor at its core. What made this definition revolutionary was its physical clarity. Previous supercluster definitions had been purely positional, grouping galaxies that were close to each other in space, without regard to whether they were gravitationally bound or even moving toward each other. The Tully et al. Definition captured the dynamical reality. Laniakea is a region of space whose matter is converging toward a common center, a gravitational basin of attraction defined by the present-day matter distribution and the velocities it induces. The boundaries of Laniakea are the surfaces on which the peculiar velocity field reverses direction, beyond which matter is flowing toward other attractors and toward other cosmic web nodes. The discovery of Laniakea and its characterization as a coherent dynamical structure illustrated a fundamental property of the cosmic web that the maps were revealing. The web is not merely a static distribution of matter. It is a dynamical system in which matter is flowing continuously from voids into sheets, from sheets into filaments, and from filaments into nodes. The present-day distribution of matter is a snapshot of this ongoing flow, frozen at the current cosmic time. The maps of galaxy positions combined with maps of peculiar velocities give a four-dimensional picture, three spatial dimensions plus the time derivative of the spatial distribution, that reveals not just where the matter is, but where it is going. The flows that the peculiar velocity surveys revealed were themselves surprisingly coherent. Matter on scales of hundreds of millions of light-years was moving in roughly organized patterns, consistent with the large-scale structure of the web, flowing away from voids and toward the filaments and nodes. But the flows were sometimes faster than the standard model predicted for the known mass distribution, suggesting either that the mass distribution was underestimated, perhaps by missing a contribution from dark matter that was not being counted, or that the dynamics of structure formation operated differently from the model's predictions at these scales. The structures so large they should not exist. The most direct challenge to the standard cosmological model from cosmic web mapping is the existence of structures on scales that the model predicts should not be present in a universe of the observed age. The cosmological principle requires that above a certain scale, called the homogeneity scale, the universe should appear statistically uniform. Structures larger than the homogeneity scale should not exist as coherent entities, because there has not been enough time since the Big Bang for gravitational processes to organise matter on those scales. The homogeneity scale has been estimated from theoretical considerations and from simulations at approximately 300 to 400 million light-years. Structures significantly larger than this should not exist as recognisable overdensities or underdensities. They do. The Sloan Great Wall at 1.37 billion light-years was the first dramatic example. Its discovery prompted a decade of debate about whether it was a genuinely coherent structure or merely a projection effect, a filamentary structure that appeared as a wall because of the geometry of the survey slice. Subsequent three-dimensional analysis showed it to be a real three-dimensional sheet of enhanced galaxy density, not a projection artifact, and genuinely inconsistent with the predictions of the Standard Model at the confidence level that cosmologists take seriously. The Hercules Corona Borealis Great Wall, identified in 2013 by Gergely Horvath and colleagues from the distribution of gamma-ray bursts used as markers of the galaxy distribution, is substantially larger, approximately 10 billion light-years in extent along its longest dimension. At this scale, the structure is not merely inconsistent with the homogeneity scale assumed in the Standard Model. It is inconsistent with the causal structure of the universe itself. 10 billion light-years is a significant fraction of the radius of the observable universe. For a structure of this size to have formed coherently would require density correlations across a scale that the Big Bang's causal horizon could not have connected. Regions separated by 10 billion light-years in the early universe were causally disconnected. No signal, no physical process, no gravitational influence could have coordinated their density fluctuations before inflation imprinted those fluctuations. Yet they appear to form a coherent structure. The Hercules Corona Borealis Great Wall has been controversial since its announcement, primarily because it is identified through gamma-ray burst positions rather than direct galaxy positions, and gamma-ray bursts are relatively rare events whose statistical distribution in a finite sample may not accurately trace the underlying galaxy distribution. But follow-up analyses using different statistical methods have consistently found a significant excess of gamma-ray bursts in the relevant sky region at the relevant redshift range, and the structure has not been definitively explained away as a statistical artifact. If it is real, it challenges the Standard Model at a fundamental level. The giant arc, reported by Alexia Lopez and colleagues in 2021, is a crescent-shaped structure of galaxies, galaxy clusters and quasars, approximately 3.3 billion light-years long at a redshift of approximately 0.8, corresponding to a look-back time of approximately 7 billion years. The giant arc is large enough that it too exceeds the expected homogeneity scale and challenges the statistical expectations of the standard lambda CDM model. Its discoverers calculated that the probability of such a structure appearing by random chance in a standard cosmological model was approximately 0.0003%, effectively zero, at the level of statistical significance that physicists use to claim discoveries. The Big Ring, reported by the same team in 2024, is a ring-shaped arrangement of galaxies and galaxy clusters, approximately 1.3 billion light-years in diameter at the same redshift as the giant arc. The proximity of the giant arc and the Big Ring in both redshift and sky position suggests they may be physically related, perhaps both components of a much larger structure whose full extent has not yet been characterized. If the two structures are parts of the same coherent entity, the combined structure would be among the largest known in the observable universe, and its existence at a look-back time of 7 billion years would be deeply problematic for the Standard Model of structure formation. What makes these large structures particularly significant is not just their individual existence, but their cumulative challenge. A single structure marginally exceeding the homogeneity scale might be a statistical fluctuation, rare but not impossible. A catalogue of structures exceeding the homogeneity scale in multiple surveys at multiple redshifts in multiple regions of the sky, discovered by multiple independent teams using multiple independent methods, is a systematic pattern that demands systematic explanation. Either the homogeneity scale has been underestimated, or the structure formation process operates differently from the standard model's predictions, or there is new physics at large scales that the standard model does not contain. The voids that are too perfect. If the overdense structures of the cosmic web challenge the standard model by being too large and too organized, the voids challenge it by being too empty and too regular. The voids of the cosmic web are not merely regions of low galaxy density, they are regions of almost no galaxy density, bounded by surprisingly sharp walls of filaments and sheets, arranged in patterns of striking geometric regularity that the standard model of structure formation does not naturally produce. The Boötes void was the first great void to be recognized as extraordinary. Discovered in 1981 by Robert Kirshner and colleagues during a survey of galaxy redshifts in the constellation Boötes, it was initially described as a spherical region approximately 250 million light-years in diameter, containing almost no galaxies. Subsequent surveys refined its dimensions to approximately 330 million light-years and confirmed that within this volume, the galaxy density was approximately 20% of the cosmic average, making it one of the least dense regions of the observable universe. The void has often been described using the analogy that if the Milky Way were located at the center of the Boötes void, astronomers on Earth would not have discovered the existence of other galaxies until the 1960s, because the nearest neighbouring galaxy would be too distant to observe with the technology available before that decade. The aspect of the Boötes void that most challenges the standard model is its size and its apparent spherical symmetry. Voids in the standard model of structure formation form through the evacuation of matter from initially underdense regions, but they grow in shapes that are influenced by the surrounding matter distribution, and typically do not achieve the near-perfect spherical symmetry that the Boötes void appears to have. The larger and more perfectly spherical a void, the less likely it is to have formed naturally through standard gravitational processes in the time available since the Big Bang. The Boötes void is not impossibly large by the standards of lambda CDM simulations, but it is at the extreme tail of the distribution, occurring in only a few % of simulated universes with standard parameters. The KBC void, identified in 2013 by Keenan, Barger and Cowie and named after its discoverers, is potentially the largest void yet identified, though its status as a coherent structure is still debated. The KBC void is an underdensity of approximately 20% below the cosmic average matter density, extending approximately 2 billion light-years in diameter, centered approximately on our own location. The Milky Way sits inside a void. This has immediate implications for our measurements of the universe's expansion rate. A local void causes the local expansion rate to be higher than the global average, because the underdensity reduces the gravitational deceleration of the local Hubble flow. The KBC void has been proposed as a partial explanation for the Hubble tension, the discrepancy between the locally measured expansion rate and the rate inferred from the cosmic microwave background. The Hubble tension is one of the most significant problems in contemporary cosmology. The locally measured Hubble constant, determined from the cosmic distance ladder using Cepheid variables and type IR supernovae, gives a value of approximately 73 kilometers per second per megaparsec. The Hubble constant inferred from the cosmic microwave background using the standard lambda CDM model gives a value of approximately 67 kilometers per second per megaparsec. The discrepancy is approximately 9%. And its statistical significance has been growing as measurements on both sides have become more precise. If we live inside a large local void, the local expansion rate would be boosted above the global average by an amount that could account for part or all of this discrepancy, without requiring any new physics in the early universe or any modification to the Standard Model's fundamental parameters. The calculations show that a void of the KBC void's estimated properties could boost the local expansion rate by approximately 1 to 2 kilometers per second per megaparsec, accounting for perhaps 1/3 to 1/2 of the Hubble tension. This is not sufficient to explain the full discrepancy, but is a meaningful contribution that would reduce the significance of the tension and potentially make it consistent with statistical fluctuations in a standard cosmological model. Whether the KBC void is real and whether its properties are as extreme as initial estimates suggested is still being debated, with more recent analyses giving a range of estimates for the void's depth and extent. The geometric regularity of voids in the cosmic web is perhaps the most puzzling of their properties. When large numbers of voids are identified in galaxy surveys and stacked on top of each other to average out the statistical noise and reveal the typical void profile, they appear remarkably spherical and remarkably uniformly structured. Their density profiles rise steeply at their boundaries, more steeply than the Standard Model predicts, and the boundary structures, the walls of filaments and sheets that surround them, are more sharply defined than simulations typically produce. The voids appear cleaner, more precisely bounded, and more perfectly spherical on average than the same structure formation physics should produce. The filaments that are actually alive. The filaments of the cosmic web are not static structures. They are active, dynamic conduits through which matter flows continuously. Gas accretes onto galaxies, and energy transfers between the cosmic web's components. Recent observations have begun revealing the filaments not as inert threads of slightly enhanced galaxy density, but as living structures with internal dynamics, temperature gradients, magnetic fields, and ongoing accretion processes that connect the intergalactic medium to the formation and evolution of individual galaxies within them. The most direct observations of filament dynamics have come from the Sunyaev-Zeldovich effect, the distortion of cosmic microwave background photons by scattering off hot electrons in the warm, hot intergalactic medium that fills the filaments. When CMB photons pass through a hot plasma, they gain energy from the electrons in the plasma through inverse Compton scattering, resulting in a distortion of the CMB spectrum at the location of the plasma. This distortion, called the thermal Sunyaev-Zeldovich effect, can be used to map the warm-hot intergalactic medium even when it is too diffuse and too cool to be detected directly in X-ray observations. In 2019, observations using the Planck satellite CMB temperature maps combined with galaxy position catalogues confirmed the existence of warm-hot intergalactic medium in the filaments between pairs of galaxy clusters. By stacking the CMB temperature signal across thousands of pairs of clusters connected by filaments, the researchers detected the thermal Sunyaev-Zeldovich signal of filament gas at a temperature of approximately 3 million Kelvin, far too cool and too diffuse to detect in X-rays from any individual filament, but measurable as a statistical average across many filaments. The result confirmed that filaments are filled with hot baryonic gas and provided the first direct measurement of this warm-hot intergalactic medium in the cosmic web. More recent observations have pushed further. In 2020, the Rosetta telescope, launched on the Spectrum Roentgen Gamma satellite, produced the deepest and most sensitive X-ray survey of the sky ever made. The Rosetta data revealed X-ray emission from individual filaments connecting the Perseus and Hubble 347 clusters, the first time that the hot gas in a filament had been directly imaged in X-rays rather than detected statistically through stacking. The filament gas was measured at a temperature of approximately 10 million Kelvin, denser and hotter than the typical warm-hot intergalactic medium, and the detection confirmed that even individual filaments contain detectable reservoirs of hot gas that can be directly observed with sensitive instruments. The gas flowing through filaments is not merely a passive tracer of the cosmic web structure. It is the fuel for galaxy formation, the raw material from which stars are made. The cold streams model of galaxy formation, developed theoretically in the 2000s and 2010s by Dipole, Boehm, and collaborators, proposes that galaxies in the early universe grew primarily by accreting cold gas that streamed in along the filaments of the cosmic web, penetrating through the hot gas halos around massive galaxies without being heated and shock compressed the way the classical picture predicted. The cold streams model resolves several puzzles about early galaxy formation, including the fact that massive galaxies in the early universe were forming stars at rates much higher than could be sustained by the gas available within their own halos at the temperatures predicted by classical accretion theory. Webb has begun providing observational evidence for cold streams in individual high redshift galaxies. Several galaxies at redshifts above 4, seen when the universe was less than 1.5 billion years old, show asymmetric gas velocity patterns and enhanced star formation along specific directions that are consistent with accretion of cold gas along filaments. The filaments are feeding the galaxies. The cosmic web is not merely a backdrop against which galaxy formation occurs. It is an active participant in galaxy formation, channeling the fuel for star formation directly into the galaxies that inhabit it. The magnetic fields in filaments add another dimension of complexity and scientific interest. The interstellar and intracluster media are known to be permeated by magnetic fields of significant strength, measured through Faraday rotation of polarized radio sources. The intergalactic medium in filaments also appears to be magnetized, with field strengths in the range of a few nanotesla, inferred from the same Faraday rotation technique applied to radio sources behind filaments. The origin of these magnetic fields is uncertain. They may have been generated in the early universe through a variety of mechanisms, including inflation-era processes, cosmological phase transitions, or the Biermann battery mechanism operating during the formation of the first structures. Or they may have been seeded by the outflows of supernovae and active galactic nuclei from galaxies and amplified by turbulence in the filament medium. Understanding the origin and evolution of magnetic fields in the cosmic web is a major open problem in theoretical cosmology, with implications for galaxy formation, cosmic ray propagation, and the early history of the universe. The nodes, where physics goes to extremes. At the intersections of filaments, where the cosmic web concentrates its mass most intensely, conditions exist that are found nowhere else in the observable universe outside of individual black holes. Galaxy clusters, the largest gravitationally bound objects in the universe, sit at the nodes of the cosmic web and contain within them a hierarchy of extreme physical environments. Temperatures of tens of millions of Kelvin in their hot intracluster gas, the largest magnetic fields on intergalactic scales, supersonic shock waves propagating through the cluster medium, and gravitational potentials so deep that they deflect light from background sources by angles measurable in arc-minutes. The mass of a typical large galaxy cluster is in the range of 10 to the 14 to 10 to the 15 solar masses, meaning 100 trillion to 1 quadrillion times the mass of the Sun. This enormous mass is distributed in 3 components. Approximately 5% is in the stars and gas of the individual member galaxies. Approximately 15% is in the hot intracluster medium, the diffuse gas that fills the space between galaxies and glows brightly in X-ray light at temperatures of 10 to 100 million Kelvin. And approximately 80% is in dark matter, distributed in an extended halo that is not directly observable, but whose presence is inferred from the gravitational effects it produces on the visible matter and on the light of background galaxies. The intracluster medium is the largest reservoir of hot baryonic gas in the universe per unit of cluster mass, and its physical state is extraordinarily complex. It is not in equilibrium in the sense of being static and quiescent. It is turbulent, heated by the mergers of subclusters that constantly assemble the cluster from smaller components, compressed and rarefied by the passage of shock waves, cooled locally by radiation, but heated globally by the energy input from central active galactic nuclei, and threaded by magnetic fields that suppress heat conduction and provide additional pressure support against gravitational collapse. Cluster mergers are among the most energetic events in the universe since the Big Bang. When two galaxy clusters merge, they collide at velocities of several thousand kilometers per second, and the collision releases kinetic energy comparable to 10 to the 63 ergs, roughly 10 million times the total energy output of the Sun over its entire 10 billion year lifetime, released in a few billion years of merger dynamics. This energy heats the intracluster medium, drives shock waves visible in X-ray images, and accelerates particles to cosmic ray energies through the diffusive shock acceleration mechanism that operates at the shock fronts. The bullet cluster, observed in detail in the early 2000s using the Chandra X-ray Observatory, provided the most dramatic visual demonstration of cluster merger physics and simultaneously the strongest direct evidence for the existence of dark matter. The bullet cluster is a system of two galaxy clusters that collided approximately 150 million years ago. The X-ray image shows the hot intracluster gas, which interacted electromagnetically during the collision and was decelerated, forming a characteristic bullet-shaped shock structure. The weak gravitational lensing map, showing the distribution of total mass, including dark matter, shows the mass concentrated in two clumps that have passed through each other and are now separated from the gas. The dark matter did not interact during the passage and continued through without decelerating. The separation between the gas and the mass distribution is direct evidence that the mass is not the gas. It is something else, something that passes through itself and through the gas without interacting, which is precisely the behavior expected for dark matter. The El Gordo cluster, discovered in 2012 using the Atacama Cosmology Telescope, is the most massive galaxy cluster known at high redshift. At a redshift of approximately 0.87, corresponding to a look-back time of approximately 7 billion years, El Gordo contains mass equivalent to approximately 2,000 trillion solar masses. Its very existence at this redshift challenges the standard model of structure formation, which predicts that clusters of this mass should not have assembled by this epoch, because there has not been sufficient time for the hierarchical merging process to build up such enormous concentrations. El Gordo is found in roughly 1 in 10 million simulated universes with the standard cosmological parameters. It is an extreme outlier, and its existence, like the Sloan Great Wall before it, points to structure formation proceeding faster and producing more massive structures earlier than the standard model predicts. The alignments that have no right to be there. Among the many surprising properties of the cosmic web revealed by detailed surveys, perhaps none is more conceptually challenging than the large-scale alignments of galaxy properties. Galaxies within filaments of the cosmic web show preferred orientations, with their shapes, their angular momenta, and the planes of their rotation all tending to align with the filaments they inhabit in systematic patterns that extend over distances of hundreds of millions of light-years. These alignments are not the result of direct gravitational interaction between neighbouring galaxies. They are correlations in the initial conditions from which the galaxies formed, preserved and amplified by the process of cosmic web assembly over billions of years, stretching across distances so vast that no physical process could have coordinated them after the universe became transparent. The intrinsic alignment of galaxies, the tendency of the shapes and orientations of physically neighbouring galaxies to be correlated, has been known since the 1980s from studies of galaxy cluster members and their surrounding environment. Galaxies in clusters tend to have their major axes aligned with the cluster's elongation, and the angular momenta of galaxies in filaments tend to be preferentially perpendicular to the filament axis. These local alignments are physically understood as arising from the tidal gravitational field of the large-scale structure, which torques the forming galaxy and influences its angular momentum through a process called tidal torque theory. The tidal field at the location of a forming galaxy is set by the surrounding mass distribution, and since that mass distribution has the geometry of the cosmic web, the alignments of galaxies reflect the web's geometry. What is not understood is the scale over which the alignments persist. Multiple analyses of large galaxy surveys, including SDSS and the kilo-degree survey, have found that intrinsic alignments are significant on scales of tens of megaparsecs, far larger than any direct gravitational interaction between galaxies could produce. The alignments appear to trace the coherent tidal field of the cosmic web on its larger scales, which is itself correlated on scales of hundreds of megaparsecs, because the web's filaments and voids extend over those distances. The implication is that the angular momenta of galaxies separated by hundreds of millions of light years are correlated, not because of any direct interaction between the galaxies, but because they formed in regions of the universe whose large-scale tidal environments were correlated through the coherent structure of the cosmic web. The alignments are not merely of academic interest for understanding galaxy formation. They are a significant systematic effect that must be accounted for in weak gravitational lensing analyses, because the intrinsic shape correlations of physically adjacent galaxies can mimic the shape correlations induced by gravitational lensing by the cosmic web. If the intrinsic alignments are not correctly modelled and subtracted from the lensing signal, they contaminate the measurement of the dark matter distribution. The largest ongoing weak lensing surveys, including DES, the kilo-degree survey, the Hyper-Suprime Cam survey, and the Euclid mission, all require careful intrinsic alignment modelling to achieve their scientific goals. And the modelling in turn requires understanding the physics of how galaxy alignments correlate with the large-scale structure of the cosmic web. The quasar alignments discovered in the 2010 S are even more mysterious. Quasars, the brilliantly luminous active galactic nuclei powered by rapidly accreting supermassive black holes, show spin axis alignments on scales of hundreds of millions of light years in several independent surveys. The most comprehensive analysis, conducted by Damien Hutzemakers and colleagues using data from large quasar catalogues, found that the position angles of quasar polarization, which traces the orientation of the jets and accretion disk, and therefore the spin axis of the central black hole, are aligned in coherent patterns over scales of 1 to 3 billion light-years. The probability of these alignments arising by random chance in an isotropic universe was calculated at approximately 1 in 10,000. The physical mechanism for these quasar spin alignments is completely unknown. The spin of a supermassive black hole is set by the angular momentum of the material that was accreted onto it over the billions of years of its growth, a process that is local and determined by the specific history of gas infall and merger activity experienced by that particular galaxy. There is no known mechanism that could coordinate the spin directions of supermassive black holes separated by hundreds of millions to billions of light years. Yet the alignments are observed. They persist in multiple independent datasets. They have not been attributed to any known systematic effect, and they align, at least in some analyses, with the large-scale structure of the cosmic web, suggesting a connection between the alignments and the primordial tidal field from which the web assembled. The voids inside the voids. One of the most striking features of the cosmic web, revealed by detailed three-dimensional maps, is its hierarchical self-similar structure. The web is not simply organized at one scale, it is organized at every scale simultaneously, with structures nested inside structures in a pattern that repeats over many orders of magnitude. Filaments within filaments, sheets within sheets, clusters within superclusters and voids within voids. The web appears to be fractal, or at least to have fractal-like properties over a range of scales. And this self-similarity is both a prediction of the standard model and, in its specific details, a probe of the underlying physics. The void-in-void structure was predicted theoretically before it was confirmed observationally. The excursion set theory of structure formation, developed by Bond, Cole, Lacey and Kaiser in the early 1990s, predicts that voids should contain subvoids, small underdense regions within larger underdense regions, organized in a hierarchical structure analogous to the hierarchical structure of halos within halos on the overdense side of the web. The prediction follows from the same mathematics of gravitational collapse and expansion that predicts the clustering hierarchy on overdense scales, and it implies that the void population should be characterized by a specific void-in-void probability and a specific void size function that can be compared with observations. Observational confirmation of the void hierarchy came gradually as survey depth and volume increased. The initial detection of individual large voids in relatively shallow surveys gave way as surveys deepened, to the recognition that those large voids contain smaller voids, which in turn contain still smaller, underdense regions down to the scale of the smallest voids detectable in the available data. The void catalogue from the SDSS DR7 redshift survey produced by Pan and colleagues contained thousands of voids spanning a range of sizes from tens to hundreds of megaparsecs, and analyses of the catalogue confirmed that the void size distribution matched the predictions of excursion set theory at the level of precision available from that dataset. But the details of the void hierarchy also revealed departures from the simplest predictions. The boundaries between voids and the surrounding filament walls are sharper in observations than in simulations, suggesting that the process of matter evacuation from voids and accumulation in the surrounding walls is more efficient or more complete than the standard structure formation model produces. The interior structure of voids shows less substructure than simulations predict. The observed voids are emptier on their interiors than simulated voids, with galaxy counts in void interiors falling below simulation predictions. This could indicate that the galaxy formation process is suppressed more strongly inside voids than the standard model predicts, perhaps because the ultraviolet radiation field inside voids is different from the average, or because the gas dynamics in low-density environments are not adequately captured in current simulations. The largest voids, those exceeding a few hundred megaparsecs in size, show a particularly interesting property. They appear to be shielded from the reionizing ultraviolet radiation field that pervades the denser regions of the intergalactic medium. The reionization of the universe, the process by which the neutral hydrogen that filled the universe after recombination was ionized by the ultraviolet radiation from the first stars and quasars, was not uniform. Dense regions near the first luminous sources were ionized first. The interiors of large voids, far from any ionizing sources, may have been among the last regions to be ionized, and the gas in these regions may retain chemical and thermal properties closer to the pre-reionization state than gas in any other accessible environment. Observations of the Lyman alpha forest, the absorption pattern produced in the spectra of background quasars by the neutral hydrogen along the line of sight, have been used to map the ionization state of the intergalactic medium as a function of position, and have found evidence for patchy reionization consistent with this picture, with the interiors of large voids being among the most recently ionized regions. The cosmic web in the early universe. The cosmic web we observe in detail today formed over billions of years from small initial perturbations. But the process of web formation did not wait until the present. The structures that we now see as clusters and superclusters and great walls began assembling long before they reached their current maturity. And the question of how early in the universe's history the cosmic web began to emerge is one of the central observational and theoretical questions in modern cosmology. Before Webb launched, the consensus expectation was that the cosmic web at high redshifts would be a much less organised, much more diffuse, and much more irregular precursor of its present-day form. At a redshift of 2, when the universe was approximately 3 billion years old and roughly a quarter of its current age, protoclusters, the seeds of today's galaxy clusters, were expected to be loosely assembled collections of star-forming galaxies connected by diffuse gas, not yet collapsed into the bound, virialized structures of today's clusters. At a redshift of 6 or 7, corresponding to the universe's first billion years, even the protoclusters were supposed to be barely discernible overdensities in a largely smooth background, with the filamentary structure of the web just beginning to emerge from the primordial density field. Webb has found something different. At redshifts above 6, corresponding to ages of the universe of less than 1 billion years, Webb has detected not isolated galaxies, but organised groups and protoclusters of galaxies that appear more massive, more chemically enriched, and more morphologically organised than the standard model predicted for their age. Some of these early structures show multiple galaxies within projected distances of a few hundred kiloparsecs, forming dense associations that are already on their way to becoming the galaxy clusters of the present day at an epoch when the standard model suggests the clustering should be just beginning. The detection of what appear to be cosmic web filaments in the early universe is even more remarkable. Several observational programs using Webb and ground-based instruments have found evidence for filamentary arrangements of galaxies at redshifts above 5. The most direct detection came from observations of Lyman alpha emitters, galaxies glowing brightly in the ultraviolet Lyman alpha emission line of hydrogen, which trace the dense and ionized regions of the early intergalactic medium. These Lyman alpha emitters are found preferentially in elongated, filament-like configurations at high redshift, suggesting that the cosmic web's organizational geometry was already present when the universe was only a billion years old. The JWST deep field observations have extended this picture further. In the first year of Webb science operations, multiple programs identified extended filamentary structures at redshifts above 6, using the positions of faint galaxies and active galactic nuclei. One particularly notable structure, reported in 2023, consists of a chain of 6 galaxies at a redshift of approximately 6.6, aligned in a filament-like arrangement spanning approximately 3 megaparsecs, with the galaxy masses and star formation rates consistent with material flowing along a cosmic web filament and accreting onto the member galaxies. The existence of such organised structures at these early epochs pushes against the boundaries of what the standard model of structure formation can accommodate. The model predicts that the cosmic web emerges from the growth of primordial perturbations over time, with larger and more organised structures forming later and smaller and less organised ones forming earlier. Finding organised filamentary structures at the universe's earliest accessible epochs implies either that the model underestimates the rate of structure growth, that the initial perturbations were larger or differently distributed than the model assumes, or that the process by which structure assembles operates differently from the model's predictions in the first billion years. The simulations that cannot keep up. The standard tool for testing theories of cosmic structure formation is the cosmological simulation, a numerical calculation in which the universe is represented as a three-dimensional box filled with particles representing dark matter, ordinary matter, and sometimes radiation, whose positions and velocities are evolved forward in time under the influence of gravity, hydrodynamics, and a suite of physical processes that govern gas cooling, star formation, and feedback from supernovae and active galactic nuclei. These simulations have become extraordinarily sophisticated over the past 3 decades, progressing from simple dark matter-only calculations run on single workstations to multi-billion particle hydrodynamic simulations run on the world's largest supercomputers for months at a time. The flagship simulations of the current era, including Illustrise TNG, Eagle, Simba, and their successors, model volumes of several hundred megaparsecs on a side at resolutions sufficient to resolve individual galaxies and, in some cases, the interstellar medium of those galaxies. They reproduce many observed properties of the galaxy population with impressive accuracy: the galaxy mass function, the stellar mass to halo mass relation, the colour bimodality of the galaxy population, the morphological mix of spirals and ellipticals, and the general properties of the star formation main sequence. These successes confirm that the simulations capture the dominant physical processes governing galaxy formation, even if the specific implementations of those processes in the subgrid prescriptions for star formation and feedback involve numerous approximations and free parameters. But when the simulations are compared with observations of the cosmic web specifically, and not just with the galaxy population, systematic discrepancies emerge that persist across simulation codes, and that have grown more obvious as observational data have improved. The most persistent discrepancy concerns the larger structures. When the three-dimensional galaxy distribution in simulations is analysed using the same statistical tools applied to observational surveys, the simulations consistently produce fewer structures as large and as coherent as the Sloan Great Wall, the Giant Arc, and similar observed structures. The simulations produce some large structures, as expected from the statistics of Gaussian random density fields. But the probability of finding structures as large and as statistically significant as those observed in the real universe is consistently a few percent or less in standard simulation volumes. The discrepancy at the void side of the web is equally persistent. Simulated voids are emptier than observed ones in some measures and less empty in others, depending on the specific statistic used and the specific tracer population. But the broad pattern is that simulated voids are less perfectly spherical, have less sharply defined boundaries, and show more internal substructure than the observational data indicate. The simulated warm-hot intergalactic medium in filaments is present and detectable, but its density and temperature distribution differs from the observations of filament gas in ways that reflect imperfect modelling of the feedback processes that heat and distribute gas in the intergalactic medium. The simulations also struggle with the cosmic web in the early universe. At redshifts above 4, corresponding to the first 1.5 billion years of cosmic history, the simulations that have been calibrated against the present-day galaxy population typically predict a much less organised web than what Webb and other high redshift surveys are finding. The early galaxies in the simulations are less massive, form fewer stars, and are less clustered than the observed population. And the filamentary structures connecting them are less coherent and less extended. This is the same problem that has been described in terms of the individual galaxy properties, the excess of massive early galaxies that the simulations do not produce, but it manifests at the cosmic web level as a failure to produce organised large-scale structure as early as the observations require. The response of the simulation community to these discrepancies has been to refine the physical prescriptions in the simulations, increase the resolution and volume, and add new physics. The Millennium Simulation Series, the Illustris TNG series, the Flamingo simulation released in 2023, and the Millennium TNG project have all pushed the boundaries of what is computationally accessible, using volumes of several gigaparsecs on a side with billions of particles to sample the statistics of rare large structures more accurately. These larger simulations have somewhat reduced the tension with observations of large structures by simply providing better statistics, but they have not eliminated the tension. The structures that are observed at the edge of the homogeneity scale remain more common in the real universe than in the simulations, and the early cosmic web remains more organised than the simulations produce. A different response has been to question whether the standard cosmological model itself needs modification. Several groups have proposed extensions to lambda CDM, that could produce larger and earlier structures while remaining consistent with the strong constraints from the cosmic microwave background. Modifications to the primordial power spectrum, adding extra power on large scales beyond what the standard scale invariant Harrison-Zeldovich spectrum predicts, would enhance structure formation on those scales and could explain some of the observed superstructures. Modifications to dark matter, making it self-interacting or giving it a small but non-zero decay rate, would change the small-scale structure of dark matter halos and could affect the properties of filaments and voids. Early dark energy, a form of dark energy present in the early universe that subsequently faded, would affect the growth rate of structure in ways that could produce earlier and more massive structures than the standard model allows. None of these modifications has yet been confirmed observationally, but none has been definitively ruled out, and the cosmic web observations are providing new constraints that will increasingly discriminate among them. The practical conclusion from the comparison between simulations and observations is that we are in a period of productive tension. The simulations are good enough to reproduce the broad features of the cosmic web and to identify where the discrepancies lie, but not good enough to explain them within the standard framework. The observations are precise enough to quantify the discrepancies, but not yet precise enough to definitively identify their physical origin. The next generation of simulations, running on exascale computers with improved physical prescriptions and larger volumes, combined with the next generation of surveys from DSI, Euclid, and the Rubin Observatory, will either close the gap or sharpen it into a genuine crisis for the standard model. The dark matter skeleton nobody can see. The cosmic web that galaxy surveys map is the luminous web, the distribution of visible matter in the form of stars and gas in galaxies. But the web's underlying skeleton, the framework that determines where the filaments run and where the voids lie, is made not of visible matter, but of dark matter, which interacts with ordinary matter only gravitationally and emits no light across any wavelength. The dark matter web is the structure that organizes the visible web, preceding it in time, generating the gravitational potential wells into which gas falls and galaxies form, and determining the geometry of the cosmic architecture over the largest scales. Mapping the dark matter web directly is one of the central technical challenges of modern cosmology, and the tools being developed to accomplish this are revealing a dark architecture that is simultaneously more complex and more structured than any previous characterization suggested. The primary technique for mapping the dark matter distribution is weak gravitational lensing, the subtle distortion of the apparent shapes of background galaxies caused by the gravitational bending of light by the dark matter distribution between those galaxies and Earth. The distortion is called weak because it is small. A galaxy that would appear perfectly circular in the absence of lensing appears slightly elliptical, with the elongation direction and magnitude determined by the tidal field of the dark matter along the line of sight. No individual galaxy's true shape is known, so the distortion cannot be measured from a single galaxy. It can only be measured statistically by averaging the shapes of many galaxies in a region of sky and looking for a coherent signal of aligned ellipticities that would indicate systematic lensing by a foreground mass concentration. The Kilo-degree survey, the Hyper-Suprime Cam Subaru strategic program, and the Dark Energy Survey have all produced detailed weak lensing maps of the dark matter distribution over significant fractions of the sky. These maps reveal the dark matter cosmic web directly, showing the same network of filaments and voids that galaxy surveys trace with luminous matter, but now extending the picture to the dark matter that makes up roughly 80% of the total mass. The agreement between the dark matter maps from lensing and the galaxy distribution maps from spectroscopic surveys is itself a confirmation of the standard picture. The visible galaxies are biased traces of the underlying dark matter distribution, more concentrated in the peaks of the dark matter web and absent from the voids, but following the same large-scale geometry. The Euclid mission, designed from the outset for high-precision weak lensing science, is producing dark matter maps of unprecedented area and depth. Euclid's primary lensing survey covers approximately 15,000 square degrees of sky, roughly 1/3 of the full sky, imaging more than 1 billion galaxies with sufficient angular resolution to measure their shapes precisely. The sheer statistical power of 1 billion galaxy-shape measurements, combined with careful control of systematic effects in the point spread function modelling and the intrinsic alignment corrections, produces a weak lensing signal with a signal-to-noise ratio far exceeding all previous surveys. The dark matter maps from Euclid are showing the Webb skeleton at multiple redshifts simultaneously, building a three-dimensional picture of how the dark matter web has grown and changed over the past several billion years. What these dark matter maps reveal, combined with the galaxy distribution maps, is a picture of the cosmic web as a biased sampling of the underlying dark matter structure. The filaments of visible galaxies are thinner and more concentrated than the dark matter filaments that contain them. The nodes of galaxy clusters sit at the peaks of the dark matter density field, but extend over smaller volumes than the dark matter halos they inhabit. The voids in the galaxy distribution correspond to voids in the dark matter distribution, but are slightly deeper, because galaxies are preferentially absent from low-density regions even more strongly than the dark matter is. The ratio between the galaxy density and the dark matter density, called the galaxy bias, is not constant across the web. It depends on the local density, the local velocity field, the large-scale environment, and the properties of the galaxies being counted. In the dense nodes and filaments of the web, galaxies are dense relative to the dark matter, and the bias is high. In the voids, galaxies are even more absent than the dark matter, and the bias is low or even negative in some measures. The scale and environment dependence of the bias is one of the most complex aspects of the relationship between the luminous web and the dark matter web, and modelling it correctly is essential for extracting accurate cosmological constraints from galaxy surveys. The most dramatic feature revealed by the combination of galaxy surveys and weak lensing dark matter maps is the existence of dark matter filaments connecting galaxy clusters that have not yet accumulated enough gas and galaxies to be detectable in galaxy surveys alone. These dark matter bridges, connecting pairs of clusters with tenuous threads of dark matter that contain little or no luminous matter, are visible in the lensing maps as subtle enhancements in the dark matter surface density between cluster pairs. Their detection requires stacking the lensing signal over many cluster pairs to achieve sufficient signal to noise. But such stacking analyses have now been performed successfully in multiple surveys, confirming the existence of dark matter bridges at statistically significant levels. The dark matter web is more connected than the visible galaxy web, with dark matter threads connecting objects that appear isolated in galaxy catalogues. The missing baryons are inside the web. For decades, astronomers faced a puzzle that seemed to strike at the heart of the standard cosmological model. More than half of all the ordinary matter in the universe was missing. Not dark matter, which has always been understood to be undetectable by most means. Ordinary baryonic matter, the protons and neutrons and electrons that make up stars, gas, and everything visible, which the Big Bang nuclear synthesis calculations predict should constitute approximately 5% of the universe's total energy density. When astronomers tallied up all the baryonic matter they could find in stars, in the gas within and around galaxies, and in the hot gas of galaxy clusters, they accounted for only about half of what should be present. The other half was simply absent from the observational census. The resolution to the missing baryon problem was proposed theoretically in the 1990s and early 2000s. The missing baryons are in the warm-hot intergalactic medium, the diffuse plasma that fills the filaments and sheets of the cosmic web at temperatures of approximately 100,000 to 10 million Kelvin. At these temperatures, the gas is too cool and too diffuse to emit significantly in X-rays, which are the primary observational tool for hot diffuse gas in galaxy clusters and groups. But it is also too hot and too ionized to be easily detected in absorption against background sources at ultraviolet or optical wavelengths, where cold neutral gas is commonly observed. The warm-hot intergalactic medium occupies a temperature and density regime that was observationally inaccessible to the instruments available in the 1990s, creating an observational blind spot that coincided precisely with the location of the missing baryons in the cosmological simulations. The detection of the warm-hot intergalactic medium has been one of the observational success stories of the past decade, achieved through multiple independent techniques that together have now convincingly confirmed that the missing baryons are indeed in the cosmic web's filaments. The thermal Sunyaev-Zeldovich effect, discussed in the context of filament detection, has now been used not just to detect gas between specific pairs of clusters, but to map the warm-hot intergalactic medium over wide areas of the sky by cross-correlating CMB temperature maps with galaxy catalogues. The cross-correlation signal detects the average thermal Sunyaev-Zeldovich distortion at the positions of galaxies and galaxy groups, where the warm-hot intergalactic medium is expected to be concentrated. Absorption line spectroscopy of distant quasars provides a complementary technique. When the ultraviolet light from a background quasar passes through a filament of warm-hot intergalactic medium containing highly ionized oxygen, the oxygen ions absorb specific ultraviolet wavelengths, producing absorption lines in the quasar spectrum. The highly ionized oxygen ions present in gas at temperatures of 300,000 to 1,000,000 Kelvin produce a specific set of absorption features at ultraviolet wavelengths that are accessible to the Hubble Space Telescope's cosmic origin spectrograph, and at higher redshifts to ground-based spectrographs. Systematic surveys of quasar spectra for these highly ionized metal absorption features have detected dozens of individual filaments of warm-hot intergalactic medium, measuring their temperatures, densities, and chemical compositions directly. The total amount of baryonic matter in the warm-hot intergalactic medium, inferred by combining the various detection techniques and extrapolating to the full population of filaments and sheets, accounts for approximately 40 to 50% of the total expected baryonic density. Combined with the baryons in stars and cold gas in galaxies, approximately 10 to 15%, and the baryons in the hot gas of galaxy clusters, approximately 5 to 10%, the total now accounts for most of the expected baryonic budget with reasonable consistency. The missing baryon problem has not been completely solved, with uncertainties in the warm-hot intergalactic medium measurements and in the corrections for gas outside the survey regions, but the broad conclusion is robust. The missing baryons are in the cosmic web's filaments, precisely where the simulations predicted they would be. The implications of this resolution extend beyond simply accounting for the baryonic census. The warm-hot intergalactic medium in filaments contains metals, elements heavier than hydrogen and helium produced in stars and expelled by supernovae and active galactic nuclei. The presence of metals in the intergalactic medium at the low densities characteristic of filaments requires that those metals were transported there from the galaxies where they were synthesized, which means that the outflows from galaxies have propagated into the cosmic web and enriched the intergalactic medium on scales comparable to the interfilament separations. The scale of this enrichment and the timescales over which it occurred are important constraints on the strength and geometry of galactic outflows, and on the history of feedback from star formation and active galactic nuclei in galaxies throughout cosmic history. The chemical composition of the warm-hot intergalactic medium in filaments is therefore a record of the feedback history of galaxies, written in the intergalactic medium of the cosmic web. The web is shaping every galaxy within it. The cosmic web is not merely the environment in which galaxies happen to reside. It is an active physical agent that shapes the properties of galaxies throughout their lives, determining their star formation rates, their morphologies, their gas contents, and their ultimate evolutionary fates through a combination of gravitational, hydrodynamic, and radiation field effects that operate across a wide range of spatial scales and timescales. The relationship between a galaxy's position in the cosmic web and its physical properties is one of the most active areas of current galaxy evolution research, and the detailed maps of the web from recent surveys are enabling this relationship to be characterized with a precision not previously possible. The most fundamental connection between the cosmic web and galaxy properties is the dependence of galaxy mass on the properties of the dark matter halo in which the galaxy resides. Galaxies form and grow within dark matter halos, and the mass of a galaxy is strongly correlated with the mass of its host halo through the stellar mass to halo mass relation. The halo mass, in turn, is determined by the local density environment. Dense regions of the cosmic web, the filaments and nodes, contain more massive halos that form earlier and have accreted more mass over their history. Galaxies in dense environments are therefore on average more massive, older in their stellar populations, and more likely to be elliptical in morphology than galaxies in the underdense void interiors. This broad trend, the morphology density relation first noted by Dressler in 1980, reflects the deep connection between the cosmic web's architecture and the galaxy population it hosts. But the connection between web environment and galaxy properties extends beyond the broad mass morphology trend to subtler effects that reveal the specific physical mechanisms by which the web influences galaxy evolution. Galaxies in filaments show enhanced star formation rates compared to galaxies in the general field at the same stellar mass, an effect that has been observed in multiple surveys and interpreted as the result of gas accretion along the filaments feeding enhanced star formation in the member galaxies. Galaxies at the edges of filaments, where the gas density begins to transition toward the lower densities of the walls and sheets, show intermediate star formation rates and intermediate morphological properties, forming a transition population between the active star-forming spirals of the void walls and the quiescent ellipticals of the cluster nodes. The transition from active star formation to quiescence, called galaxy quenching, shows a strong dependence on the cosmic web environment that goes beyond the simple halo mass dependence. Galaxies of the same stellar mass and the same halo mass quench their star formation earlier and more completely if they are located closer to a filament or node than if they are located in a void. This environmental quenching, operating over and above the mass quenching that would occur based on the galaxy's own properties, indicates that the web environment affects galaxy evolution through physical channels that are not captured by the halo properties alone. The leading physical candidates include strangulation, the removal of the warm gas surrounding galaxies by interaction with the filament medium, cutting off the supply of gas that would cool and replenish the cold gas reservoir for star formation. RAM, pressure stripping, the direct stripping of cold gas from galaxies by the pressure of the warm-hot intergalactic medium as the galaxy moves through it. And the effects of the ultraviolet radiation field, which is stronger in denser regions near active galaxies and quasars, and suppresses gas cooling. The spin alignments of galaxies with the cosmic web provide another layer of connection between web architecture and galaxy properties. Galaxies in filaments tend to have their angular momentum axes perpendicular to the filament direction, so that they spin around an axis pointing away from the filament. This alignment is strongest for lower mass galaxies and weakens for more massive ones. The physical interpretation is that lower mass galaxies were torqued by the large-scale tidal field of the filament during their formation, acquiring angular momenta aligned with the tidal field. More massive galaxies, which formed through more mergers and more complex accretion histories, have had their angular momenta randomized by the merger events and retain less memory of the initial tidal torque alignment. The mass dependence of the alignment therefore encodes information about the relative importance of smooth accretion versus mergers in building the angular momenta of galaxies of different masses. Galaxy groups and clusters, the most massive and most overdense concentrations in the web, represent the extreme end of environmental effects. Galaxies that fall into clusters undergo a rapid transformation. Their star formation is quenched by ram pressure stripping and strangulation within approximately 1 to 2 billion years of infall. Their morphologies change from disk-dominated to bulge-dominated through tidal interactions and harassment, and their gas contents are reduced to levels far below those of comparable mass field galaxies. The pre-processing of galaxies in the filaments before they reach the cluster itself is a subject of active research, with evidence accumulating that some degree of quenching begins in the filament environment before the galaxy reaches the cluster virial radius, blurring the sharp distinction between cluster and field environments that earlier models assumed. The cold spots that should not be cold. The cosmic microwave background sky contains temperature anomalies at large angular scales that have no satisfactory explanation in the standard cosmological model, and that appear to be connected, at least in some cases, to specific large-scale structures in the cosmic web. The most famous of these is the CMB cold spot, a region of the CMB sky in the direction of the constellation Eridanus that is approximately 70 microkelvin colder than the surrounding region over an angular scale of about 10 degrees. The cold spot was identified in WMAP data and confirmed in Planck data, and its combination of depth and angular size makes it statistically unlikely at the level of approximately 1 to 2% in the standard model. Several physical explanations have been proposed for the cold spot, and the one most directly connected to the cosmic web is the integrated Sachs-Wolf effect from a large supervoid along the line of sight. As CMB photons pass through a void, they first gain energy falling into the void's gravitational potential well, and then lose energy climbing out of it. In a static universe, these two effects would exactly cancel, leaving no net temperature shift. But in an accelerating universe dominated by dark energy, the potential wells decay over time as the void grows and the surrounding walls expand outward. When CMB photons climb out of a void whose potential well has become shallower during their transit time, they lose less energy than they gained on entry, resulting in a net energy gain, which corresponds to a hot spot in the CMB rather than a cold one. Conversely, a supervoid can create a cold spot in the CMB through the time reversal of this effect, though the sign depends on the specific timing of the dark energy domination relative to the void's growth history. The Eridanus supervoid, first identified in galaxy surveys in 2015 by Finelli and colleagues and subsequently characterized in more detail by Kovacs and collaborators, is a roughly spherical underdensity extending approximately 1.8 billion light-years in diameter at a redshift of approximately 0.2, corresponding to a look-back time of approximately 2.7 billion years. The void is real and has been confirmed in multiple independent surveys, including 2MASS, WISE and the Dark Energy Survey. The question is whether it is deep enough and well positioned enough to produce the observed CMB cold spot through the integrated Sachs-Wolf effect. Calculations based on the measured void density profile give an expected temperature decrement of approximately 10 to 20 microkelvin, which is significantly less than the observed 70 microkelvin deficit. The Eridanus supervoid accounts for some of the cold spot, but not all of it. The remainder is either a statistical fluctuation in the CMB itself, a residual from foreground subtraction, or a signature of physics beyond the standard model. The importance of the cold spot for cosmic web science is not primarily in its own explanation, but in what its investigation reveals about the connection between the CMB and large-scale structure. The integrated Sachs-Wolf effect is a probe of the evolution of the gravitational potential in the late universe, which depends on the competition between gravitational collapse and dark energy acceleration. Measuring the cross-correlation between CMB temperature maps and galaxy survey maps gives a direct measurement of this effect, averaged over many structures, providing a constraint on the dark energy equation of state and the matter density that is independent of the standard geometric dark energy probes. The detection of the integrated Sachs-Wolf effect in cross-correlations of WMAP and SDSS data in 2003 was one of the early confirmations of the existence of dark energy, and subsequent measurements with progressively larger surveys have refined the constraint. Beyond the Eridanus supervoid and the CMB cold spot, there is a broader pattern of anomalies in the large-scale CMB temperature map that appears correlated with the large-scale structure of the matter distribution. The CMB quadrupole and octopole, the two lowest-order multipole moments of the CMB temperature fluctuations, are anomalously aligned with each other and with the ecliptic plane and the direction of the CMB dipole in a way that is statistically unlikely in the standard model. This axis of evil, as it has been called, might reflect the influence of the local large-scale structure on the observed CMB, either through the integrated Sachs-Wolf effect from the local void structure, or through some other interaction between the local matter distribution and the primordial CMB fluctuations. The possibility that our position in the cosmic web, inside or near a large local void like the KBC void, systematically biases our measurements of the CMB by adding a large-scale signal from the integrated Sachs-Wolf effect of the void has been explored theoretically and found to be capable of producing some of the observed CMB anomalies, though not all of them. The dipole anomaly and the direction the universe is flowing. The CMB dipole is the largest temperature anisotropy in the cosmic microwave background, a pattern in which one hemisphere of the sky is systematically warmer than the other by approximately 3.3 millikelvin. This dipole was interpreted from its first detection as a Doppler shift, caused by our motion relative to the rest frame of the CMB. The Milky Way is moving at approximately 369 kilometers per second toward the constellation Leo, and this motion blue shifts the CMB in the forward direction and red shifts it in the backward direction, producing the observed temperature gradient. The CMB dipole direction defines what is called the kinematic dipole, the direction of motion of our local region of the universe relative to the CMB rest frame. This motion is the result of the combined gravitational pull of all the matter in the observable universe on our local supercluster, and its direction and magnitude encode information about the large-scale distribution of matter in the universe. The dominant contribution to our motion comes from the Great Attractor Complex and its surrounding superstructures, as established by the peculiar velocity surveys that map the flows leading to the discovery of Laniakea. But there are also contributions from structures at greater distances, and measuring the full velocity vector of our local region requires understanding the gravitational influence of structures across a wide range of distances. The controversy surrounding the dipole involves the behaviour of the kinematic dipole as measured from progressively more distant samples of objects. If the CMB dipole correctly identifies our motion relative to the cosmic rest frame, then the dipole measured from any cosmologically distributed sample of objects, such as distant galaxies or quasars, should point in the same direction as the CMB dipole and have the same magnitude. This is because the sample is distributed across all directions on the sky, and the kinematic aberration produced by our motion shifts the apparent positions of sources systematically in a way that creates a dipole in the number counts with the same direction and amplitude as the CMB dipole. Multiple analyses of large quasar and radio galaxy catalogues have found kinematic dipoles that point in broadly the same direction as the CMB dipole, but with significantly larger amplitudes than expected. The excess amplitude suggests either that the local universe has a coherent bulk motion relative to the CMB rest frame that is larger than the standard model predicts from the known mass distribution, or that the measured dipole includes contributions from intrinsic clustering of the source populations that contaminate the kinematic signal, or that there is new large-scale physics at work that the standard model does not describe. The most comprehensive analysis, combining multiple catalogues covering different sky areas, redshift ranges and wavelength regimes, has found persistent evidence for a kinematic dipole excess at the level of 2 to 4 times the expected amplitude in some samples, though with significant variations between samples that reflect the difficulties of controlling for intrinsic clustering and selection effects. The statistical significance of the excess varies from approximately 2 to 4 sigma, depending on the sample and the analysis method, making it a tantalizing but not yet definitive anomaly. If the kinematic dipole excess is confirmed by future surveys with better controlled samples and larger sky coverage, it would imply that the large-scale matter distribution in the universe is less homogeneous than the standard model predicts, with coherent density fluctuations on scales comparable to or exceeding the Hubble radius. This would be a direct violation of the cosmological principle on the largest scales, and would require either a modification of the standard inflationary cosmology that generates the primordial density fluctuations, or a fundamental revision of our understanding of the universe's large-scale structure. What the Webb tells us about dark energy. The cosmic web is not merely a structure formed by the competition between gravity and the expansion of the universe. It is a probe of the nature of the expansion itself, specifically of the dark energy that drives the universe's current accelerated expansion. The geometry of the web, the statistics of its voids and filaments and clusters, and the way those statistics evolve over cosmic time all depend on the properties of dark energy in ways that can be measured and used to constrain the dark energy equation of state and its possible time variation. The most powerful dark energy probe from cosmic web mapping is the baryon acoustic oscillation scale, the preferred separation distance of approximately 490 million light-years imprinted on the galaxy distribution by the acoustic oscillations of the primordial plasma before recombination. This characteristic scale, encoded as a subtle enhancement in the galaxy correlation function and the galaxy power spectrum at the corresponding separation, acts as a standard ruler. Because the physical size of the acoustic horizon at recombination is determined by well-understood physics and measured accurately from the CMB, the angular and redshift separations corresponding to the baryon acoustic oscillation scale at different redshifts give direct measurements of the angular diameter distance and Hubble parameter as functions of cosmic time, which together determine the expansion history of the universe and constrain the dark energy equation of state. The DASI first-year baryon acoustic oscillation measurement, released in 2024, used the positions of 6.5 million galaxies, quasars, and Lyman alpha forest absorbers to measure the baryon acoustic oscillation scale at multiple redshifts spanning the range from 0 to 4, providing the most comprehensive picture of the universe's expansion history ever assembled from a single survey. The result was in mild but noteworthy tension with the predictions of a cosmological constant model of dark energy, the best fit dark energy equation of state parameter from DASI alone, fitting the data to a model in which dark energy's equation of state can evolve with time rather than remaining fixed at -1 as the cosmological constant requires, suggested that dark energy may be evolving, with its equation of state being less negative in the past than at present. The statistical significance of this deviation from the cosmological constant was approximately 2 to 3 sigma, not sufficient for a definitive claim of discovery, but sufficient to attract significant attention and motivate follow-up analyses. The combination of DASI's baryon acoustic oscillation measurements with other cosmological probes, including supernova distances from the Dark Energy Survey and the Union 3 compilation, and CMB measurements from Planck, did not decisively resolve the question. Different combinations of datasets gave different levels of tension with the cosmological constant and different best fit values for the evolving dark energy parameters, reflecting the different systematic errors in each data set and the different sensitivities to the dark energy evolution at different redshifts. The overall picture from the combined data sets was suggestive of evolving dark energy, but not at sufficient significance to claim detection. The statistical power to resolve the question of whether dark energy is a cosmological constant or something more dynamic will come from the full 5-year DESI dataset, from Euclid's galaxy clustering measurements, from the Rubin Observatory's weak lensing and galaxy clustering combination, and from future surveys such as the spectroscopic photometric instrument for the dark energy experiment on the Roman Space Telescope. Together, these surveys will measure the baryon acoustic oscillation scale and the growth of structure to precisions of a few tenths of a percent at multiple redshifts, providing constraints on the dark energy equation of state and its time variation that are 10 to 20 times tighter than the current best measurements. If dark energy is evolving, these surveys will detect it. If it is a cosmological constant, they will confirm it at that level of precision. The growth of the cosmic web is itself a dark energy probe that complements the geometric baryon acoustic oscillation measurement. The rate at which structures grow in the universe, characterizing how rapidly matter clusters under gravity, depends on the competition between gravitational attraction and the dark energy's anti-gravitational effect. The stronger the dark energy, the more it suppresses the growth of structure. Measuring the growth rate from the cosmic web using the redshift space distortions induced by the peculiar velocities of galaxies provides a constraint on the combination of the growth rate and the amplitude of matter fluctuations that is sensitive to modifications of gravity as well as to dark energy properties. Current measurements of the growth rate from galaxy surveys show mild tensions with the predictions of general relativity and the standard cosmological model, with the measured growth rate appearing slightly lower than predicted in some analyses. Whether this reflects a genuine departure from general relativity, a modification of dark energy, or systematic errors in the measurements is one of the key questions that future surveys are designed to answer. The tension that will not go away. The cosmic web maps have not resolved the Hubble tension. They have complicated it by revealing that the local universe is structured in ways that affect the local measurement of the expansion rate. The Hubble tension, the discrepancy between the locally measured Hubble constant of approximately 73 kilometers per second per megaparsec and the Planck CMB inferred value of approximately 67 kilometers per second per megaparsec, is currently the most significant unresolved discrepancy in cosmology, with statistical significance above 5 sigma, after accounting for systematic uncertainties in the most careful analyses. The cosmic web's role in the Hubble tension is primarily through the KBC void and the possibility that we live in a locally underdense region that has a higher local expansion rate than the cosmic average. As discussed in the chapter on voids, a local void can boost the locally measured expansion rate by an amount that depends on the void's depth, size, and our position within it. The calculations for the KBC void give a boost of approximately 1 to 2 kilometers per second per megaparsec, which reduces the tension but does not eliminate it. If the local void is deeper than current estimates suggest, the boost could be larger and the tension could be reduced to an insignificant level. But the current observational constraints on the void depth do not support a boost large enough to fully explain the tension. Several analyses of the local large-scale structure have attempted to model the full three-dimensional matter distribution in our cosmological neighbourhood and calculate its contribution to the local expansion rate. These analyses use peculiar velocity surveys, galaxy density catalogues, and gravitational reconstruction methods to estimate the gravitational influence of the known structures within a few hundred megaparsecs of the Milky Way. The reconstructed peculiar velocity at our location, which represents the deviation of our local Hubble flow from the global average typically falls in the range of a few hundred kilometres per second, consistent with being inside a moderate local underdensity, but not large enough to explain the full Hubble tension through local structure alone. The cosmic web maps are also contributing to the Hubble tension discussion through the baryon acoustic oscillation measurements, which provide a geometric measurement of the expansion history that is in principle independent of the local distance ladder calibration. As discussed in the previous chapter, the Dark Energy Spectroscopic Instrument, DRSI, baryon acoustic oscillation results show hints of evolving dark energy that, if confirmed, would represent a modification to the cosmological model that could potentially accommodate a higher expansion rate without modifying the early universe physics that the Planck CMB analysis assumes. If dark energy is evolving from a less negative equation of state at earlier times to a more negative one at later times, the expansion history between the CMB epoch and the present could be different from the cosmological constant prediction in a way that changes the predicted local expansion rate. The most comprehensive treatment of the Hubble tension within the cosmic web context requires combining the constraints from the local distance ladder, the baryon acoustic oscillations from galaxy surveys, the CMB power spectrum from Planck, and the maps of local large-scale structure from peculiar velocity surveys and galaxy density catalogues into a single, coherent analysis. No such analysis has yet produced a fully satisfactory resolution. The tension persists at a level that makes it unlikely to be explained by statistical fluctuations, requires either a systematic error in one or more of the measurements that has not yet been identified despite years of searching, or new physics that modifies the standard cosmological model in a specific and constrained way. The cosmic web maps provide three potential contributions to the resolution. First, they constrain the local large-scale structure and its contribution to the locally measured expansion rate, potentially explaining part of the discrepancy through the void effect. Second, they provide baryon acoustic oscillation measurements at multiple redshifts that constrain the expansion history and might reveal departures from the cosmological constant that close the gap between the early universe and late universe expansion rate estimates. Third, the growth rate measurements from the Webb's peculiar velocity field test general relativity and the growth of structure in ways that could reveal modifications to gravity or dark energy that solve the tension through a change in the physical framework. Whether any of these contributions will ultimately resolve the tension, or whether the tension will require a more fundamental revision of cosmological physics, remains one of the most important open questions in the field. What has become increasingly clear is that the Hubble tension is not a single measurement problem, but a network problem, embedded in the same large-scale structure that the cosmic web maps are now revealing in detail. Each method of measuring the expansion rate samples a different part of the web, at different redshifts, with different sensitivities to environment and structure. The local distance ladder is built within a specific region of the cosmic web, influenced by nearby voids, filaments, and clusters. The CMB, by contrast, measures the universe at a time before the web fully formed, inferring the expansion rate indirectly through a model that extrapolates forward across billions of years of structure formation. The tension may therefore reflect not just a mismatch in measurements, but a mismatch in how these different regimes are connected through cosmic evolution. There is also growing interest in whether subtle selection effects tied to the cosmic web environment could bias local measurements. For example, the galaxies used to calibrate supernova distances may preferentially reside in certain environments that are not fully representative of the cosmic average. If those environments are systematically associated with slightly different expansion histories or gravitational potentials, this could introduce a bias that is difficult to detect but significant at the level required to explain part of the tension. Cosmic web maps, by providing a detailed environmental classification of galaxies, offer a way to test and potentially correct for such effects. Another avenue being explored is the role of anisotropy in the local expansion field. If the expansion rate is not perfectly isotropic on scales of a few hundred megaparsecs due to the influence of large structures in the cosmic web, then measurements in different directions could yield slightly different values of the Hubble constant. Early studies suggest that any such anisotropy is small, but the increasing precision of both observations and reconstructions means that even subtle directional variations can now be probed. If detected, these variations would add a new layer of complexity to the interpretation of the Hubble tension. The connection between the Hubble tension and the growth of structure is also becoming more important. Measurements of the growth rate, often parameterized by combinations like FS8, provide an independent test of the consistency between the expansion history and the formation of the cosmic web. Some analyses have found mild tensions between the observed growth rate and the predictions of the standard model, raising the possibility that both the Hubble tension and the growth tension are symptoms of the same underlying issue. If so, the solution may require a modification that simultaneously affects expansion and structure formation, such as a new component of dark energy or a change in the laws of gravity. Finally, the increasing precision of cosmic web mapping is enabling consistency tests that were not previously possible. By reconstructing the density and velocity fields in the local universe and comparing them with the predictions of different cosmological models, researchers can directly test whether a given model can simultaneously match the observed structure and the measured expansion rate. These joint constraints are far more powerful than those derived from any single dataset alone, and they are likely to play a central role in resolving the tension in the coming years. In this evolving picture, the cosmic web is not just a complicating factor, it is a diagnostic tool. It provides the context within which all measurements of the expansion rate must be interpreted. As that context becomes clearer, the space of possible explanations for the Hubble tension will narrow. Whether the final answer turns out to be a subtle systematic effect, an environmental bias, or genuinely new physics, the path to that answer runs through the structure of the universe itself. What comes next for cosmic cartography? The mapping of the cosmic web is not finished. It is accelerating. The surveys currently underway and the missions currently operating or about to begin will expand the three-dimensional census of the universe's structure by factors of 10 to 100 in both volume and precision within the next decade. Moving from the first detailed maps of local large-scale structure to a comprehensive atlas of the universe's architecture across most of cosmic history. The scientific questions that these expanded maps will address include some of the deepest in cosmology: the nature of dark energy, the validity of general relativity on cosmological scales, the origin of the largest structures, and the connection between the cosmic web and the properties of individual galaxies. The Rubin Observatory, now beginning science operations at the Vera C. Rubin Observatory in Chile, will survey the entire southern sky visible from its location repeatedly over 10 years, building a photometric catalogue of approximately 20 billion objects to unprecedented depth. Its primary dark energy probe is the weak gravitational lensing of background galaxies by the foreground dark matter distribution, which will produce a dark matter map of the southern sky to a depth and precision far exceeding the current Euclid lensing survey. The combination of Rubin's southern lensing map with Euclid's northern and southern coverage will together produce a full sky dark matter atlas of the cosmic web, directly imaging the dark matter skeleton of the universe's largest structures from the present epoch back to a redshift of approximately 2. Dark Energy Spectroscopic Instrument, DIC's ongoing 5-year survey, scheduled to complete in 2026, will measure spectroscopic redshifts for approximately 40 million galaxies and quasars, producing a 3-dimensional map of the universe's matter distribution spanning a comoving volume of approximately 70 cubic gigaparsecs. The statistical power of the sample will enable measurements of the baryon acoustic oscillation scale at multiple redshifts to sub% precision, the growth rate from redshift space distortions to comparable precision, and the cross-correlations between the galaxy distribution and the CMB, weak lensing and thermal Sunyaev-Zeldovich maps to new levels of sensitivity. The DSEA dataset will be the primary spectroscopic resource for cosmic web science in the first half of the 2020s, and its combination with the Euclid photometric survey will produce a more complete picture of the web's geometry and dynamics than any single survey alone. The Square Kilometre Array, or SKA, now beginning construction in South Africa and Australia, with first science expected in the late 2020s, will extend cosmic web mapping into the radio wavelength regime, with capabilities that complement optical and infrared surveys in several important ways. The SKA will map the distribution of neutral hydrogen gas in galaxies across a wide range of redshifts through the 21 centimetre emission line, providing a tracer of the cold gas reservoir that is complementary to the stellar mass tracer of optical surveys. The SKA will also enable high-precision measurements of the Faraday rotation of polarized radio sources by the intergalactic magnetic field, providing a three-dimensional map of the magnetic field threading the cosmic web that will constrain models of magnetic field generation and evolution in the early universe. And the SKA's radio continuum surveys will produce catalogues of radio galaxies and active galactic nuclei that can be used to measure the dipole anisotropy and test the isotropy of the universe on the largest scales. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey the sky in the near-infrared from space with a wide field of view comparable to Euclid, but a significantly larger primary mirror. Its high-latitude survey will produce a weak lensing catalogue of approximately 1 billion galaxies at greater depth than Euclid, and its multi-object spectrograph will measure spectroscopic redshifts for tens of millions of galaxies in multiple redshift ranges. The combination of Roman's lensing and spectroscopic datasets with those from Euclid and DESI will provide redundancy against systematic errors and enable consistency tests that will separate genuine cosmological signals from instrumental and astrophysical systematic effects. Looking further ahead, the proposed Stage 5 spectroscopic experiment Mega Mapper would extend the spectroscopic frontier to redshifts above 2, with a statistical sample of galaxies at the epoch when the cosmic web was actively assembling, bridging the gap between the low redshift web of current surveys and the high redshift proto-web being revealed by James Webb Space Telescope. And the proposed CMB-S4 experiment would produce CMB lensing and thermal Sunyaev-Zeldovich maps at an angular resolution and sensitivity an order of magnitude better than Planck, enabling direct mapping of the warm-hot intergalactic medium and filaments across a wide range of environments and redshifts. Together, these future facilities will transform cosmic web mapping from a field of impressive first discoveries into a precision discipline capable of testing cosmological models at the level of detail needed to distinguish between the standard lambda CDM model and its leading competitors. Beyond these flagship missions, an ecosystem of complementary surveys and theoretical efforts is emerging that will deepen and refine the picture even further. High-resolution hydrodynamical simulations are being run at scales that match the observational data sets, allowing for direct one-to-one comparisons between simulated universes and the real one. These simulations are increasingly incorporating more realistic models of feedback from star formation and black hole activity, which are essential for understanding how baryonic physics reshapes the underlying dark matter framework. As observational precision improves, these small-scale processes become critical, because even subtle mismatches between theory and observation can bias cosmological inferences if not properly accounted for. At the same time, machine learning techniques are beginning to play a central role in analysing the enormous data sets produced by these surveys. Neural networks are being trained to identify filaments, classify environments, reconstruct density fields, and even infer cosmological parameters directly from raw data. These methods offer the potential to extract more information from the data than traditional techniques, particularly in the nonlinear regime where analytic models break down. However, they also introduce new challenges, especially in ensuring interpretability and controlling systematic uncertainties. Another important frontier is time-domain cosmology within the cosmic web. As surveys repeatedly scan the sky, they will capture transient events such as supernovae, tidal disruption events, and variable active galactic nuclei across different environments in the web. This opens the possibility of studying how cosmic structure influences not just the static properties of galaxies, but their time-dependent behavior. The connection between environment and transient phenomena may provide new insights into galaxy evolution and the role of large-scale structure in shaping it. Ultimately, the goal is not just to map the cosmic web in ever greater detail, but to understand it as a unified physical system. Each new data set adds another layer to that understanding, tightening constraints, revealing tensions, and sharpening the questions that remain unanswered. As the observational and theoretical tools continue to improve in parallel, the field is moving toward a point where even small deviations from the standard model will become impossible to ignore. When that threshold is crossed, the cosmic web will no longer just hint at new physics, it will demand it. The universe is structured all the way down. The mapping of the cosmic web has revealed something that neither the theoretical nor the observational community fully anticipated. The universe is organized at every scale simultaneously, and the organization at each scale is connected to the organization at every other scale through a web of correlations that spans from the scale of individual galaxies to the scale of the observable horizon. The filaments shape the galaxies they contain. The voids determine the chemical state of the gas within them. The nodes transform the galaxies that fall into them. The large-scale tidal field aligns the spins of galaxies separated by hundreds of millions of light-years. The baryon acoustic oscillation scale imprinted in the first 380,000 years is still visible in the distribution of galaxies today. The same dark matter overdensities that seeded the first galaxies are the nodes of the web we map today. This coherence is not surprising in the sense that it follows from the standard cosmological model. A universe that grew from Gaussian random initial conditions under gravity and dark energy should develop a structured web whose properties are correlated across scales because the underlying density field is correlated. The remarkable thing is not that the correlations exist, but that they are as strong as they are, extending to scales larger than the model predicts, appearing at redshifts earlier than the model allows, and producing alignments that the model cannot fully explain. The universe is more organized than it should be, and that extra organization is a signal pointing toward physics beyond the standard model. The specific nature of that new physics is not yet known. It might be a modification to the primordial power spectrum generated during inflation, adding extra power on large scales that seeds the formation of larger and earlier structures. It might be a modification to dark matter, making it self-interacting or giving it properties that change the internal structure of halos and filaments. It might be a modification to gravity on large scales, changing the growth rate of structure in ways that are consistent with the CMB, but produce a different web structure at late times. It might be a form of dark energy more complex than the cosmological constant, evolving over time and affecting the competition between gravitational attraction and cosmic expansion in ways that leave signatures in the web's geometry and statistics. Whatever the new physics turns out to be, if it exists, the cosmic web is the observational arena in which it will be discovered. The web is the largest experiment in the universe, the product of 14 billion years of gravitational, hydrodynamic, and dark energy physics, operating on the full volume of the observable cosmos. The maps we are now assembling are the first complete data from that experiment. And what the data show, in multiple independent probes at multiple scales and multiple epochs, is that the standard model of cosmology is correct in its broad outlines and incomplete in its details. The universe is structured in a way that the model captures well, but not perfectly. And the places where it deviates from the model's predictions are pointing systematically toward the same conclusion. There is more to the story. The cosmic web is not a backdrop. It is a message. And we are only now learning to read it. What makes this realization even more profound is that the cosmic web is not merely a static structure imprinted in space. It is a dynamic system, continuously evolving, redistributing matter and energy across vast distances over cosmic time. Galaxies are not isolated islands drifting passively within it. They are active participants in a network of flows. Gas streams along filaments into galaxies, fueling star formation. Feedback from supernovae and active galactic nuclei pushes material back out, enriching the intergalactic medium and altering the thermal and chemical state of the surrounding web. This constant exchange creates a feedback loop between small-scale astrophysical processes and the largest structures in the universe. The web is not just shaping galaxies. Galaxies are, in turn, shaping the web. One of the most striking developments in recent years has been the ability to directly observe these flows. Through increasingly sensitive instruments, astronomers have begun to detect the faint glow of hydrogen gas tracing the filaments themselves, as well as the absorption signatures they leave in the light of distant quasars. These observations reveal that the filaments are not empty bridges, but dense, dynamic environments where matter is funneled with surprising efficiency. The picture that emerges is one of a living structure, where matter is constantly in motion, guided by gravitational potentials that extend across millions of light years. At the same time, numerical simulations have reached a level of sophistication that allows them to model this complexity in extraordinary detail. Large-scale simulations now incorporate not only gravity, but also hydrodynamics, radiation, magnetic fields, and the complex physics of galaxy formation. When these simulations are compared with observations, the agreement is often remarkable, but the discrepancies are where the most interesting clues lie. Subtle mismatches in the distribution of galaxies, the temperature of intergalactic gas, or the alignment of structures can point to missing physics or incorrect assumptions. Each discrepancy is a potential window into something deeper. Another layer of insight comes from the study of cosmic voids, the vast regions of space that contain very little matter. Once thought to be relatively unimportant, voids are now recognized as some of the most sensitive probes of cosmology. Because they are underdense, they are less affected by the nonlinear clustering that complicates the interpretation of dense regions. This makes them cleaner laboratories for testing theories of gravity and dark energy. The shapes, sizes, and distributions of voids carry information about how structure has grown over time, and early results suggest that they too may be hinting at deviations from the simplest models. The alignment of galaxy spins with the large-scale structure adds yet another piece to the puzzle. According to standard theory, these alignments should be relatively weak and largely washed out by nonlinear evolution. Yet observations increasingly suggest that coherent alignments persist over enormous distances. This raises questions about the initial conditions of the universe and the processes that amplified these correlations over time. If confirmed, such alignments could provide a new and powerful probe of the early universe, complementing the information encoded in the cosmic microwave background. The role of dark matter in all of this cannot be overstated. It is the scaffolding upon which the cosmic web is built, dominating the gravitational potential that shapes the distribution of visible matter. Yet despite its central importance, its nature remains one of the greatest mysteries in physics. Different models of dark matter predict different small-scale structures within the web. from the smoothness of filaments to the abundance of small halos. By studying these details with increasing precision, astronomers hope to narrow down the possibilities and perhaps even identify the true nature of this elusive component. Dark energy, too, plays a crucial role, particularly in the late-time evolution of the web. As the expansion of the universe accelerates, it counteracts the pull of gravity, slowing the growth of structure and stretching the web over time. The precise way in which this happens depends on the properties of dark energy, which remain largely unknown. By mapping the web at different epochs, astronomers can trace how structure growth has changed over time, providing constraints on the behavior of dark energy and its possible evolution. Looking ahead, the next generation of surveys promises to transform our understanding even further. Projects that map billions of galaxies across vast volumes of space will provide an unprecedented view of the cosmic web in 3 dimensions. At the same time, new techniques such as intensity mapping and gravitational lensing tomography will allow us to probe the distribution of matter, including dark matter, more directly than ever before. These observations will not only refine our picture of the web, but also test the fundamental assumptions of cosmology with unparalleled precision. In this sense, the cosmic web is becoming something more than just an object of study. It is becoming a tool, a way of probing the deepest questions about the nature of reality. It encodes information about the initial conditions of the universe, the properties of its most mysterious components, and the laws that govern its evolution. By learning to decode this information, we are effectively turning the universe itself into an experiment, one that has been running for billions of years, and whose results are written across the sky. The implication is both humbling and exhilarating. Humbling because it reminds us that our current theories, as successful as they are, capture only part of the story. Exhilarating because it means that the answers to some of the most profound questions in physics may already be within reach, hidden in the patterns of galaxies and the structure of the cosmic web. The challenge now is not just to observe more, but to understand more, to develop the theoretical frameworks and analytical tools needed to interpret what we see. As this effort continues, one thing is becoming increasingly clear. The cosmic web is not just a consequence of the universe's evolution. It is a record of that evolution, a kind of cosmic memory that preserves the imprint of processes that occurred billions of years ago. Every filament, every void, every cluster carries information about the forces that shaped it. By studying these structures in detail, we are, in a very real sense, reading the history of the universe written on the largest possible canvas. And that is why the deviations matter so much. If the universe were perfectly described by our current models, the cosmic web would simply confirm what we already know. But it does not. It contains anomalies, tensions, and patterns that do not quite fit. These are not failures, they are opportunities. They are the places where new physics can emerge, where our understanding can deepen, where the next breakthroughs can occur. The cosmic web, in the end, is not just a structure. It is a signal, subtle, complex, and still only partially understood. It is telling us that the universe is richer, more interconnected, and more intricate than our simplest models suggest. And as our ability to observe and analyze it continues to improve, that signal will become clearer. The message is already there, encoded in the distribution of matter across billions of light years. We are only beginning to decipher it. The map is the discovery. The act of mapping the cosmic web is itself the scientific achievement, not merely the instrument by which some other discovery is made. For most of human history, the universe beyond the Milky Way was known only as a collection of faint smudges in the sky, unresolved and uncatalogued, their true nature debated until the 20th century. The recognition that those smudges were galaxies, each containing billions of stars at distances of millions to billions of light years, was the first expansion of the known universe's scale beyond what unaided human intuition could previously comprehend. The second expansion is happening now. The cosmic web surveys of the past 20 years have revealed that those galaxies are not scattered randomly through space, but are organized into the largest coherent structure in the observable universe. A structure that stretches from our local neighborhood to the limits of the observable cosmos, built from filaments and voids and nodes whose geometry is determined by the physics of the universe's first fractions of a second, and whose evolution is driven by the dark energy that will determine its ultimate fate. This is not just a fact about where the galaxies are. It is a fact about the universe's identity, its history, and the principles that govern its operation. What the maps reveal at the level of scientific surprise and intellectual consequence is a universe that is simultaneously more structured and less understood than the decades before mapping would have suggested. The standard model of cosmology, lambda, CDM, is one of the most precisely tested theories in all of science. It correctly predicts the cosmic microwave background, the abundance of light elements, the expansion history of the universe, the formation and evolution of galaxies from small seeds, and the broad properties of the cosmic web. Its success is genuine and its foundations are solid, and yet the maps show structures larger than it predicts. They show alignments it cannot explain. They show voids sharper than its simulations produce. They show an early universe more organized than its timeline allows. They show a local expansion rate higher than its early universe physics implies. Each of these discrepancies, taken individually, might be a statistical fluctuation or a measurement artifact. Taken together as a systematic pattern appearing in multiple independent surveys using multiple independent techniques at multiple redshifts and scales, they constitute a coherent message that the model is incomplete. The cosmic web is the universe's self-portrait, drawn in the positions and motions of hundreds of millions of galaxies across billions of light years. We have been mapping it for decades and are now for the first time beginning to see the full picture with enough clarity to read what it says. What it says is that the universe is stranger than the model, more structured than expected, and more connected across scales and epochs than any simple picture of hierarchical assembly from random seeds would suggest. The map is not wrong, the universe is surprising, and the science of the cosmic web is, for precisely that reason, the most exciting frontier in cosmology.